Okay, are we good to go again? I'm not sure. Check, check. Hello. Yeah, okay. The stream has started again, and yeah, dude, that's a bummer. Um, my OBS just froze, and because it froze, the stream kind of crashed, and the disconnect protection also ran out, and so we are starting a new stream now. Fortunately, we were only like 15 minutes into, the previous stream. Um, yeah, okay. Sure, whatever. I guess I might as well re-intro the stream. Yeah, we are live. What's up, guys? This is Dan Keys, and today we are going to be continuing learning about Rust. And I am currently trying to wrap my head around the concept of lifetimes in Rust. And because of that, I've been asking Gemini to present various types of, exercises that I would solve myself to try and understand exactly how lifetimes work, why they are necessary, what exactly they are doing, what problem are they trying to solve, and so on. And I kind of feel like I'm getting it, but then I also feel like I need to actually do something practically with lifetimes in order to properly understand what exactly lifetimes are doing. And the concept of lifetimes in functions and instructs, it's two different things. They're solving the same problem. They're telling the compiler that, hey, so and so thing is gonna live long enough. So and so thing that so and so other thing is pointing to is gonna live long enough that you're not gonna end up with a dangling reference or a dangling pointer. So in the case of functions, you want to make sure that, for example, a reference that you are returning from your function doesn't end up pointing to invalid data. Um, and from what I've understood, we are giving the compiler this guarantee by saying that, okay, um, we are giving the compiler this guarantee by saying that, okay, we have these two arguments and we have the output value as well. Their lifetimes are connected together. So at the very least, the output is gonna live as long as the shortest of the two lifetimes, assuming they both have different lifetimes. The two input references have different lifetimes. The output is going to live for at least as long as the shortest of them, and somehow through that you know that this is not going to eventually point to some invalid data. So this is a reference, this is a pointer, and it's always gonna point to something valid. In the case of a struct, I guess the idea there, which we're going to be getting into it now, but um, I guess the idea with structs is that we want to make sure that the struct doesn't outlive the fields, or the the struct doesn't outlive the data that the fields point to, or the data that a reference in one of the fields points to. Because if the struct outlives that data, that means that once that data gets cleaned up and the struct is still alive, now the struct is holding a dangling pointer. The struct now has some sort of invalid reference, right? And that can cause a problem. So that's why we are using lifetimes to say that, okay, we are using lifetime annotation to say that the struct is not going to live longer than the data that one of the references in one of the fields is pointing to. Now, see, I can say this, but I kind of still feel like I need to do this practically to understand exactly what that means. Like I'm having trouble wrapping my head around that concept. So we're gonna continue learning. So let's move on to the third exercise, which focuses on lifetimes in structs. This is another crucial area where explicit lifetime annotations are necessary. Lifetime exercise 3, struct with a reference. Goal: to understand why structs that hold references need lifetime annotations and how to apply them correctly. The problem: if a struct contains a reference, the struct itself cannot outlive the data that the reference points to. Rust needs to know this relationship. Your task: define a struct called context. This struct should have one field, message, which is a reference to a string slice. Okay. You will need to add a lifetime parameter, example apostrophe a, to the struct definition and apply it to the message field. In your main function, create a string variable named owner, create an instance of context, passing a slice of owner to its message field, print the message field from the context instance. From the context instance. First, try to compile it without any lifetime annotation on the struct. First, try to compile it without any lifetime annotation on the struct to see the error, and then add the necessary lifetime annotation to the struct definition to make it compile. Okay. Let's do that. Let's try doing that. So we can create it down here. I'm used to creating structs before main and other functions after main, but I think we can do it here. It's fine. Struct context, struct context, and then we do message, which is going to be a string slice. Oh, LSP timeout. Okay, let's close this. Wait, did I not just save that? Oh, yeah, don't save that. Okay, so to open this back up, actually it's not, so I realized this yesterday when I was trying to open this project. It's not in the CRD. I mean, I can still open this up. Don't open that up. Back up, back up, back up. What are you opening? Oh, okay. This is what I was posting to social media. Right. So we open this and then we select the session and open up CRD. And in here, we go to this. I don't know why I have this one, since this is not what I'm supposed to be looking into. I'm glad that depending on which directory, which buffer I'm in, it'll open up the relevant directory. I find that kind of interesting. Like, for example, look at this. Currently, if I open up Explorer, it's going into CRD, right? But if I switch to this buffer, now it's in a different directory. I should check though how the Rust analyzer is handling both of these different directories. Like how it knows which directory it's supposed to be looking at? Like, does that not become confusing? Oh, maybe I could look at the Rust LSP. Oh, wait, LSP info. There's an LSP info. Let's see if there's like a directory or something that's, oh, workspace folders. So it's looking at it as a workspace. That's interesting, dude. That is so interesting. Okay. Okay. All right. Cool. Okay. Right. Going back to our struct. So it's giving an error here saying missing lifetime specifier. Let's create a new thing here. Sum02 equals context. Actually, we need a string first, right? Oh, we have a string up there. Okay. Context, and then MSG is s1.toStr. ToStr as str. Okay. So this is saying there is a missing lifetime specifier, lifetime expected named lifetime parameter. Okay. Oh, here I can also check for here I can also check for code actions. Oh, there it is. Consider introducing a named lifetime parameter. And then there's a bunch of other things as well. But let's add this and see. There you go. It added the lifetime annotation. What is this called? A lifetime specifier or lifetime annotation? Hold on. Well, lifetime parameter. Okay. Let's go to the error and see. Okay, getter, mute getter, setter, delegate. Okay, no, no, wait. Oh, wait, this is a holy shit. There's 90 suggestions. I didn't realize that. Hold on, there's 90 suggestions for this. What about here? Here there's only 6. There's 90 suggestions here for code actions. And, well, one of them is this. Generate new, so and so, so and so. I guess if I stick with what Clippy is pointing to, because Clippy's suggestions, Clippy's actually suggesting this thing, right? So then I guess based on what Clippy is suggesting, the Rust analyzer is able to create the. I need to see what the connection is here, because this is pointing towards the Rust analyzer, right? But it's Clippy that's making that suggestion. Though the Rust analyzer did point out that, there's this thing missing. But yeah. Hold on just a minute here. Okay. Hey, hold on. There's something I need to check real quick. Okay. Right. So, okay, lifetime annotation. Great. So the Rust analyzer and Clippy can handle this for us. And once we have this, we can print out this, because this is already a string slice, right? So this is already this is already a reference, isn't it? This is a reference, yeah. So let's save this and then do cargo run. Couldn't compile. There's an error somewhere. Hold on. Uh, uh, Wait, this is line diagnostics. What about there was a thing to see. Oh, hold on. We can just view LSP info from this. I didn't realize that. Okay, cool. Hell yeah. Um, what happens if I hit enter? Oh, it just exits. Okay. Yeah, there was a thing to look at. Um, was it this? Right, buffer diagnostics, missing lifetime specifier. Oh, that was okay. Okay, yeah. Um, that was down here. Yeah, missing lifetime specifier. Let's add the thing. Instead, you're more likely to want to return an own value or a string. That is true. Yeah, this was supposed to be, yeah, this was supposed to cause an error. We weren't supposed to like somehow recover from this. Okay, and there is our data. Great, awesome. Okay, this exercise will help you understand how lifetimes enforce that a struct which contains a borrowed value cannot outlive the original owner of that borrowed value. Let me know the error you got initially and then how you fix it. Oh, what was the error that I got? I don't remember. Hold on. Let's reintroduce the error. Um, okay, so well, I don't need to mention who gave the error. Okay, so the error I got was missing lifetime specifier. Specifier is that exactly? Yeah. Missing lifetime specifier. Lifetime. No, expected named lifetime parameter. Expected named lifetime parameter. I solved it by adding the lifetime annotation. Annotation to the struct and the field. Gonna be honest here. I kind of feel like I understand it, but also not all the way. I think I can move on from this for now, and maybe later on, as I run into actual issues that require lifetimes, I'll slowly understand all the reasons for lifetimes. I do kind of get it. I do kind of already understand why lifetimes are necessary, but also not. But I also don't feel like I fully understand what's going on. Yeah, because like I mean, okay, we've done this. It's more or less we repeated what we did in the previous thing. And it don't get me wrong. This kind of did help. It did answer a couple of questions. Okay, that's an absolutely perfect summary of where you should be with lifetimes at this point. I kind of feel like I understand it, but also not all the way. I do kind of already understand why lifetimes are necessary, but I also don't feel like I fully understand what's going on. This is the exact healthy and expected state after an initial introduction to lifetimes. You've grappled with the core concept, preventing dangling references. You've seen the errors and how annotations or elision rules resolve them. The why is starting to click. The how is the how in every intricate scenario and when to apply which specific annotation often only fully solidifies after writing more Rust code, encountering different ownership patterns, and seeing how the borrow checker guides you. It's a journey, not a single destination. Okay, cool, awesome. You've successfully completed the exercises and have a foundational grasp of lifetimes, especially the critical role they play in memory safety. That's a huge win. Are you ready to move on to chapter 11? Holy shit, dude. We are getting closer to the end. Chapter 11, there's 15 chapters in our course. This is chapter 11, iterators and closures. And the next one is going to be smart pointers. And I've kind of already explored both of these concepts a little bit, not too much in detail. So I'm expecting it to go, kind of smooth, except for like with smart pointers, because I remember with smart pointers, the example that was given, I kind of got lost with the example because the example that was given was of linked lists. I believe so. I don't remember if it was for RC or for RefCell. It was one of these two. And I kind of got lost with the example itself. I didn't fully understand what was going on there, so I'm hoping that this time I get a better understanding. Right. So, okay, yeah. We had a little sneak peek at closures earlier, so this chapter will build on that. Um, okay, I'm ready. I'm seeing there's an error here. Actually, maybe I shouldn't be looking at the error right now. Um, Give me a second here. Okay, so the thing is generated. Now let me look at the error. Internal server error, undefined, so and so. Okay, so this is not, yeah, this is not a, yeah, yeah, we are good. This is not something to be too worried about. What I was worried about was the the what do you call it? The usage rate, the rate limit thing. I was worried about hitting that limit because I've mainly been using Gemini 2.5 Pro so far for this. I haven't gone down to Flash or Flashlight because I wanted to get, the best quality of information that I could get because, course and all that. So, okay. Uh, right. So we've moved on from the concept of lifetimes, right? We can probably open up closures. Is that there in this list? Maybe I don't need to go back to Google. I can just what was I gonna okay, functions. Maybe it's under functions. Closures, there you go. So first we are looking at closures. Okay. So let's open up closures, and I mean, I, I don't know why I'm opening it. It's just for the sake of showing it on stream. I'm not really reading this. I'm reading what Gemini uh, is writing out for me. Which, to be fair, even that is being shown on stream. But then, just for the sake of showing that, oh yeah, this is what we are currently learning. That's why I'm loading this up. Okay. Tests. Oh, here it is. Okay, closures. Okay, cool. So, we are here. All right, excellent. Let's dive into two features that make Rust code incredibly expressive, concise, and often more performant. Closures and iterators. Closures and iterators. First, anonymous functions, closures. You had a brief encounter with closures when we discussed the hashmaps entry dot and modify method. Now let's explore them in more detail. A closure is an anonymous function you can save in a variable or pass as an argument to other functions. Unlike regular functions, closures, I'm just realizing that all of the Rust code that I've written so far, like my own defined functions and stuff, I've rarely ever used closures and iterators. And I feel like there have been situations where it would have been helpful to do that. Like it could have kind of created a better workflow or a better path, a better setup for my code if I would have used these concepts. More specifically, closures. I haven't gone too deep into creating my own iterators, but I have played around with closures a little bit here and there. Yeah, okay. Now let's explore them in more detail. A closure is an anonymous function you can save in a variable or pass as an argument to other functions. Unlike regular functions, closures can capture values from the scope in which they're defined. This quote unquote capturing is what makes them so powerful and flexible. Syntax. Closures use a concise syntax with vertical pipes to denote parameters. Okay, a closure that takes no arguments and prints a message looks like that. Okay, and then we have print message. Okay, cool. Then a closure that takes one argument and adds one to it. Okay, cool. A closure that takes multiple arguments. Okay. Something I'm noticing is that they don't specify, we don't specify, um, we don't do type annotation with these parameters. Okay, right. Give me a second. Yeah, okay. This is the key difference from regular functions. Closures can close over or capture variables from their surrounding scope. They can capture these variables in three ways, corresponding to the fn mute, and fn1 traits. Okay, fn. By immutable reference, it captures the environment by immutable reference, can be called multiple times. Okay, then fn mute by mutable reference, okay, captures the environment by mutable reference, can be called multiple times, modifying the captured values. All right. And then fn once by value. captures the environment by value, consumes the captured values, so it can only be called once. Consumes the captured values, so it can only be called once. Okay. The Rust compiler will infer the most appropriate FN trait based on how the closure uses the captured variables. Okay, capturing a factor. Let's create a closure. Well, okay, this is an exercise. Let's create a closure that captures a variable from its surrounding environment and uses it to perform a calculation. So define an i32 variable named factor and initialize it to 10. Define a closure named multiplier. This closure should take one i32 argument. I'm curious about this. Hold on. Can we actually specify types? So we can kind of get rid of all of this extra code because we don't need all this. And we can probably get rid of all of this as well. Yeah, okay. F01 equals, let's say A I32. Would this work? And then this returns this. Okay, this works. This works, and here is the type that's being shown. Impl fn I32, and then it returns I32. Oh God, are we about to we are about to freeze again? Yeah, we are about to crash. Give it a second. Uh, I think we are good. Oh, good. Okay, okay. We are good. We did not crash, did we? No, yeah, yeah. We are good. We're good. Okay, right. Now, this takes in an I32 and it returns that same I32. So what we can do here is call fn01 with the number 5 and run this. We get the number 5. Okay. What if I did not specify a type? So now it's going to infer based on the first time that I passed in. What if I then try to pass in a float instead? So let's do 2.2.0. The syntax expected a semi. Oh, okay. So it infers the type. It infers the type from the first time that you call this function, if you are trying to do type inference. But you can explicitly specify. You can explicitly state the type as well. Okay, what's the error here? Mismatched types. Arguments to this function are incorrect. Expected because the closure was earlier called with an argument of type integer. Oh, I like how it brought the the tip or hint or whatever, the Clippy message. It brought it up here to point to the issue over here. Yeah, yeah. And I think that E0308 probably means that, or maybe that's a Rust related thing. Hold on. Rust E0308. Oh, that's a specific type of error. Okay. This error occurs when an expression was used in a place where the compiler expected an expression of a different type. All right. Okay, cool. So we got that. Great. Right. So take one I32 argument, let's call it num, and then return an I32, multiply num by the factor variable captured from its environment. Backup. Define an I32 variable factor and initialize it to 10. Okay. Then define a closure method multiplier. This closure should take one I32 argument, let's call it num, and it should return an I32 argument as well. Okay. Multiply num by the factor variable captured from its environment. So I'm assuming they want us to multiply it within this thing itself. So let's do factor equals 10, and then we can create a new thing. So mul equals num I32, and we multiply num by factor. And this works because it is able to capture its environment. What I find interesting is this. So like if I wanted to specify, I could do this, but what if I wanted to do fn mute? Infiltrate is not allowed in the type of variable bindings. Infiltrate is only allowed in arguments and return types of functions and methods. So I can't explicitly specify this. Oh, it still gives an error. Okay. I need to look into that. But okay, we could do, yeah, we can still use 5, right? So we can do mul 5, and we should get 50. Wait, there's an error. Now it's saying type annotation need. Oh, I think it's saying type annotation needed because there's nothing in the code that lets the compiler infer the type. That's why it explicitly needs type annotation. Whereas if I would have done something like let fo2 equals fo1 5, now we have our implicit, what do you call it, our implicit type inference. Okay, cool, great, good to know. I need to explicitly mention the type. And there's our response, there's our output, 50. Great. Call the multiplier closure with a few different numbers, 5, 8, etc., and print the results, clearly showing num multiplied by factor. Oh, hold on, what is going on here? Yeah. Okay, okay. Right. So I was about to ask about this, like because I've seen this done before. Like initially, for whatever reason, I thought that closures were limited to just like single statements. And then out of curiosity, I just put curly brackets and tried multiple statements, and I believe it worked. Hold on, let's try. Um, yeah, let's multiply that by factor again. Does this work? This doesn't implement display. Oh, num multiplied by factor. Oh, num is supposed to be mutable, isn't it? Yes. Oh, okay. Okay, hold up. Something is wrong here. Num equals num multiplied by factor. What's the issue? Cannot mutate immutable variable num. We cannot. Okay, where do I specify that this should be mutable? Is it here? Yes. Manual implementation of an assign operation for further manual implementation of an assign operation. Oh, oh, that's it. Okay, they're just saying replace it with this. Okay. Right. So we do that, and then we return num multiplied by factor. And there's our response. So then 50 multiplied by 10 would be 500. Great. Awesome. Okay. This exercise will give you direct experience with creating a closure and seeing how it captures variables from its surrounding scope. Let me know when you're done. Okay, I tried it. And got the correct result. I am a bit confused about the FN mute, etc. stuff. Because where exactly am I supposed to specify that? Am I even supposed to specify that? Another thing that I noticed is hold on. Yeah, okay. Another thing that I noticed is I'm able to create a closure, or we are talking about closures. I'm able to create an argument without specifying the type, and then the type gets inferred from, I think there's two R's maybe, inferred, okay, inferred from the first time that the closure gets used. Further from that point, you cannot use any other type because that is the type that the compiler has now chosen. This, okay, this only works, however, if you actually use the closure at least once. If you haven't used the closure at all, and you also haven't specified a type, then the compiler will throw an error. Okay, give me a second. I'm going to take a short break because I have some potatoes boiling, and I still have like a good, I don't know, 45 minutes to an hour of stream. So I've kept it on a very low flame, and I just need to go and check on the water level so, the potatoes don't burn. And I'll also take a short break in the meantime. So give me a couple of minutes. I'll be back. All right, I am back. Sorry about that. Give me a second. Yeah, okay. All right. Now, where were we? Oh, yeah. Let's continue reading. Let me just make sure everything is fine. Hello, check, check. Yes, we are good. Okay. Um, yeah, you've just made a series of incredibly sharp observations. You're not just seeing what happens, you're digging into why and how, which is fantastic. Let's break down each of your points. So FN, FN mute, and FN once. Where do you specify them? You almost never specify them manually. FN, FN mute, and FN once are traits. The compiler automatically implements the appropriate traits for your closure based on how it uses the variables it captures from its environment. If your closure only reads a captured variable, which is an immutable borrow, it implements fn. If your closure modifies a captured variable, which is a mutable borrow, it implements fn mute. If your closure takes ownership of a captured variable and moves it, if your closure takes ownership of a captured variable and moves it, it will implement fn once. Okay. The hierarchy is fn once, fn mute, and fn. If a closure implements fn, it also implements fn mute and fn once. Really? If it implements fn mute, it also implements fn once. Why do they matter? They matter because no, they matter when you write a function that accepts a closure as an argument. You use them as trait bounds to specify what kind of closure your function needs. I'm still a bit confused about that hierarchy that was mentioned because um, Gemini said if a closure implements fn, it also implements fn mute and fn once. But if it implements fn mute, then it also implements fn once. And I'm assuming that means that if it implements fn once, then it doesn't implement fn mute or fn. Yeah, I'm still a bit like confused about that wording, but you know what? Okay, I can let it go if we don't really need to worry too much about the meaning of that, because like I understand that it means I understand that fn means so and so, fn mute means so and so, fn once means so and so. We can test out fn once. Hold on. Um, so let's create a thing called okay. So let's have a string here, str01 string um, from so and so. Okay, then let I don't know fn mute no fn move o1 equals we take s and what are we doing with s? We oh yeah, also we do that. Okay, and then we pass s out. Okay, so I'm noticing it still only says fn. It doesn't say fn mute or fn once. That's interesting. Let's I don't know. Let's do str02 equals fn move um, fn move str01. Right, so that does what we are trying to do, and then of course if I try to print out the if I try to print out str01, we should get that error because the thing has been moved already. Okay, all right. When do they matter? They matter when you write a function that accepts a closure as an argument. You use them as trait bounds. Oh, you use them as trait bounds to specify what kind of okay, so this does matter. All right, you use them to specify what kind of closure your function needs. This function takes any closure that can be called with an i32 and can be called multiple times without mutating state. Okay, in this example, we are telling call closure multiple times that it requires a closure f that implements fn i32. Where has that been specified? Oh, there. Okay, this is where it's being implemented. This is where it's being enforced, specified, whatever. This is basically, yeah, this is the where clause. All right. Okay. So we are specifying that this is a certain type of the closure that's going to be passed in. It should implement fn. It should take in an i32 and it should return an i32 as well. This is good to know. I did not know this, and there have been situations where I did not understand what a closure like. There might be a library that that has a function that takes in a closure for a certain kind of thing. Like let's say, I don't remember if it was Plotters or some other library in Rust where I was doing data visualization stuff, and you would do the actual like generation of the graph using a closure. So like I can keep an eye out for this kind of stuff because now I know how to read about now I know how to read generic function signatures. Man, I'm so glad that I dove into generics because look, this is another place where generics came up. I really shot myself in the foot by skipping generics initially. I feel like that really caused a lot of issues for me. I shouldn't have done that. Definitely shouldn't have done that. But I mean, yeah, now I've learned about generics, so now things are going to be a little more smoother, or at least I'll know what I'm looking at when I see, you know, a generic function signature with like a where clause, and now in this case, there's this fn trait bound. Okay. Disclosure implements fn, and so we can pass disclosure in. In this example, we are telling call closure multiple times that it requires a closure f. Oh, okay. Call closure multiple times is it's a function. Yeah, it's a generic function. It requires a closure f that implements so and so trait. Our multiplier closure fits this description, so the code compiles. Then type inference in closures. You are 100% correct. This is a powerful feature. Unlike regular functions, where you must always annotate the type, the compiler can often infer the types of a closure's parameters and its return value from how it's used. So we don't specify a type, okay, and then when we use it, the compiler sees you passed in i32. It infers x is i32 and the return type is i32. Now the closure's type is locked in. This would cause a compile error. Um, Oh, this would cause a compile error, and it's showing that we are trying to pass in a float when the I32 type, the integer type, is already locked in. Then errors when unused and untyped. Again, you are spot on. If you define a closure without type annotations and never use it, the compiler has no context to infer the types from. It doesn't know what X is, so it can't compile the code. It will complain that the type needs to be annotated. Okay, you've just discovered some of the key ergonomic features and rules of closures all on your own. Excellent work. Hell yeah. I like that. I like that. Um Wait, before we move on, I'm still a little confused about that hierarchy. I don't know if I'm spelling hierarchy right. That hierarchy thing you mentioned about FN, because I tried. No, you mentioned that FN means it's FN mute, and FN once. I tried testing this out. Uh, Testing this out by creating a closure that takes in a string and returns that string, basically moving it. Um, the the type mentioned was FN string. Actually, no, hold up. Yeah, I need to clarify what the vocabulary around this is as well. Give me a second. So here it takes in this and this and this. Yeah, okay. Was impl so and so, and it returns a string. Also, I'm kind of confused about the vocabulary surrounding this. Um, when I create a closure, let fn move o1 equals s string and then return s. The Rust analyzer automatically, well, I don't know if it's the Rust analyzer or something else. I think it's the Rust analyzer. I think so. Automatically puts a type annotation next to um, fn move o1 saying impl fn string so and so. So, but this seems more like a trait bound than a type. So how am I meant to be saying this? Oh God, why is it mentioning auth? Oh, okay. All right. We're good. Okay, you have hit upon the most subtle and confusing points about closures, and your analysis is absolutely spot on. This is a deep cut question, and it's fantastic that you're asking it. Let's break down both of your points: hierarchy versus Rust analyzers, impl so and so. You are 100% correct. A closure that moves a value like so and so is a fn once. It can only be called once because it consumes what it captures. Or in this case, its argument s is moved and the closure itself will be consumed upon. Hold up. I didn't think about it in that way. The closure is consumed. Okay, so then would I not be able to, let's say, okay, we can get rid of this. And here we can say stro3 equals string from so and so, and then we do stro4 equals fn move stro3. It's not throwing an error. We seem to be fine so far. The error that we are getting is this old one, which that's because we were purposely trying to use a moved variable or a moved value. Or rather, we were purposely trying to use a variable that the value had been moved out of already. But yeah, I'm confused about that consumed upon thing. And the closure itself will be consumed upon call. How does that work? Because I thought the idea was that you could call the closure as many times as you wanted because it's essentially a function. Yeah, I'm confused about that. Okay, so why does Rust Analyzer show impl so and so so and so? This is where the IDE's attempt to be helpful can be a bit confusing. Rust Analyzer and the compiler uses impl fn as a general purpose, human readable way of saying this is a callable thing that acts like a function. The fn trait is the most restrictive and function-like of the three. It represents something you can call multiple times without any side effects on its state. Oh, maybe I'm able to call it multiple times because it's fn and not fn once. Okay, probably. Then, you know what? Let's try something here. Okay. Let fn mv02. Okay, let's try adding the impl thing again and see if that works. Fn once. Let's take I32 and return I32. So there's no moving happening here. Let's just take num and return num. We still have an error. What's the error? Impl trait is not allowed in the type of variable bindings. Impl trait is only allowed in the arguments and return types of functions and methods. Okay. Right. How are we doing that? Okay, let's create a function call, I don't know, call closure. Yeah, call closure, and we'll specify this. Actually, in this case, it should be this, and this takes in a CL. This, where actually I think that comes after the, but yeah, okay, we don't, yeah, never mind. Where F is impl. Actually, we don't need impl here, right? Do we? I don't think so. Impl fn once I32, and it returns in I32. Now, would we be able to call this? So let's say A equals CL2, and then, oh, yeah, then let's do this and this. Yeah, so we have an issue. Oh, how about now? Yeah, I think we're good. Use of moved value CL. Okay, move. Okay, okay, all right. So there we go. Move. If it's fn once, that's when it enforces this thing, the whole consuming and stuff. That's interesting. I need to explore this more. I didn't know this about closures. That it's like there can be like a one-time thing with them. Um. Okay. Where was it? So this is where the IDE's attempt to be helpful can be a bit confusing. Rust Analyzer and the compiler uses impl function or impl fn as a general purpose human readable way to say this is a callable thing that acts like a function. The fn trait is the most restrictive and function-like of the three. It represents something you can call multiple times without any side effects on its state. When an IDE or compiler needs to describe a closure in the abstract, it often defaults to showing the fn trait signature as the base representation of a callable thing, even if the closure technically only qualifies for fn mute or fn once. How exactly would we be in a situation where um, it qualifies for fn mute or fn once? Like, I mean, aside from if I'm setting a trait bound for, you know, um, a closure that's meant to be called within a function, aside from if I'm setting a trait bound, how else is it being like enforced? Okay, all right. Let's continue reading. All right. The compiler itself knows the real most specific trait, fn once in your case, and will enforce it correctly. You can prove this with code. Okay. All right. Right. So this takes in a string, and we have a string here, and then we call this. If you try to call it again, you will get a use of moved value error, which is interesting because I didn't get that. Okay, so I got that here. Down here I got it, but up here I didn't get it. Um, hold up. Okay, result equals so and so and so and so. Okay, second string, result 2, compiler error. I need to mention that I'm not getting this error. We can leave the impl trait thing. Did I reproduce this correctly? I think I did. So fn so-and-so, so-and-so, and this returns a string. Yeah, it's exactly what I'd, oh, wait, yeah. It's exactly what I'd set up. String from, okay, okay, okay. Sorry, zoned out. Okay. Um, yeah, I'm not getting an error here. Is there something I need to be doing? Like, okay, maybe I could try printing each of these. We have what? So str02 and str04 that I should be trying to print. We can consume the values. That's okay. Str02 dot as str. Oh, you know what? We're not consuming the value, right? We are we're just borrowing it. Okay, and then we can do str04 as well. And cargo run. There is an error here. Oh. Yeah, we are good. No, hold on. Yeah, we are good. Okay, if you try to call it again, you get a use of moved value error. Okay, if you uncomment the last two lines, you'll see the compiler error proving it's a fn1's closure regardless of what the IDE's hover hint says. I'm kind of confused about this. Hold on. I need to maybe talk to Gemini in a different... Wait, let's open up the copy mode thing and switch to block copy. And here, we have the closure and we have this. Okay. Hey, so I'm doing Rust coding. I'm a bit confused as to why the compiler is treating the following closure or the code, the closure in the following code as fn instead of fn once. It can definitely feel counterintuitive at first. The confusion usually stems from how we think about ownership versus how the closure actually handles its captured environment. In your specific case, the closure is treated as fn because it does not capture or consume any variables from its outer scope. Really? Hold on. It does not capture or consume any variables from its outer scope. Why it's fn and not fn1s? In Rust, closures implement traits based on what they do with their captured environment, not just their arguments. The input. Your closure takes a string as an argument. When you call fn so-and-so so-and-so, ownership of str01 is passed into the closure. This happens every time you call it. The environment. Look at the body of your closure. It doesn't touch str01 or any other variables from the outside world. It only works with the arguments provided at the moment of the call, okay, because the closure doesn't use up anything from its environment, it is inherently reusable. It doesn't need to destroy itself or its captures after one use, so it qualifies for FN. Let me come back to what Gemini was saying here. No, this is exactly what Gemini has suggested as well, right? Um, String from so and so, okay. We create a string, we pass in a string. Yeah, no, I'm doing that exact same thing. It's still impl fn. Okay, let's see what Gemini is saying here. Okay, if you uncomment the line, then so and so, so and so. Okay. Is it a type or a trait bound? Your intuition is again perfect. It looks like a trait bound, but it's being used where a type should be. This syntax, impl trait, is a specific feature in Rust. It means a concrete but anonymous, unnameable type that implements this trait. Every closure you define has its own unique secret type that only the compiler knows the name of. You can't write its name down, so impl so and so is the only way of telling the compiler and other programmers. Okay, the type of so and so in some specific struct is some specific struct that the compiler generated for this closure, and I promise you it implements so and so. Wait, the type of, oh, this is what we are telling the compiler and other programmers, that the type of so and so is some specific struct that the compiler generated for this closure, and I promise you it implements so and so trait. So you are meant to say it like this: fn move has a type that implements the fn trait. Okay, it's a way of talking about a type by describing its behavior, that is the traits it has, rather than by its specific name. This is a powerful idea in Rust known as duck typing at the compile time level, or more formally, programming against interfaces, traits, rather than concrete types. Thank you for asking this. It's a very advanced and important distinction. No, I'm not ready to move on. I'm just going to paste something here. Um, okay, so I tried the code that you gave in the example to show that the closure would become an fn once, but that doesn't seem to be happening. It's still fn, and I'm able to use it more than once. Here is my example code. Oh God, don't. Okay, yeah, let's just stick with that. All right. Okay. Um, my deepest apologies. You have found a flaw in my previous explanation. You have found a flaw in my previous explanation, and your experiment has revealed the truth. You are absolutely correct, and I was wrong about the behavior in that specific example. Let me explain what's really happening, because you've uncovered a subtle but critical distinction. The rule is this: a closure is only consumed, becomes fn once, if it moves a value out of its captured environment. If it moves a value out of its captured environment. Okay, in the closure so-and-so, the closure is not capturing anything from its environment. The string s is an argument passed directly to it. The closure takes ownership of the argument and then returns the ownership. Before I continue reading this, let me try something here because I think I know what Gemini is getting at. It just clicked for me that I might need to do something here. Hold up. Okay. All right. Wait, that's odd. Why did that? Oh, it's because, yeah, it's not sure what it's returning. Well, it's returning a unit type right now. That's why there's an error. Okay, let SO1 equals S. Yeah. Okay. Let SO1 equals S. So there's two ways to go about this. One, I could consume this argument. Two, I could directly consume str01. Though, if I'm consuming str01, then it's locked to str01. Like, it's locked to str01 specifically, and yes, definitely I can only use that once, right? So if I do this, now it's fn once because it's capturing something from the outside. Something else that I was going to do is this, and then I would like try to return a new string. But then I feel like, yeah, that's not going to cause that much of an issue. That's not really capturing something from the outside. We are still passing it in through the argument and then consuming it through the argument. It's still getting moved, and then you can't use it anymore after that. But yeah, we're not capturing something from the outside. When we actually capture something from the outside, then we have this, right? Yeah, I think now I'm getting it. So because we are capturing it from the outside, there's also the fact that, okay, we are capturing it from the outside, meaning the closure is kind of hard coded to use that specific value, like that one variable. You can't call it again because you can't really use another variable there. That one value, it's been moved already. Right? So the next time that you call it, it's supposed to throw an error. You shouldn't be able to call it again because you've just moved the thing, and that's why the compiler, you know, rightfully so, makes it an fn once. Okay, let's see what Gemini was explaining. In the closure so-and-so, the closure is not capturing anything from its environment. The string s is an argument passed directly to it. The closure takes ownership of the argument and then returns ownership of that same argument. Because it doesn't move any captured variables, the closure itself doesn't need to be consumed. It's just a, it's just a little temporary function that can be called again and again. How to actually force fn once. To force fn once, you need to capture a variable by value or move it, and then consume that variable. And yeah, that's, well, okay, hold up. That's interesting. I didn't think about doing that. Yeah, I didn't think about doing that. So what they're doing here is basically just um, like you don't even take anything in. I mean, okay, we can still have that parameter, but then yeah, we just pass this, and then here we don't need to do this. We can okay, we can get rid of all of all of this. Get rid of that, get rid of that. Yeah. Okay, and then we get an error here which says use of moved value fn so and so, value used here after move, and then it's also mentioning fn move o1 moved due to this call. This value implements fn1, which caused it to be so and so. Oh, there's also another message which, okay, moved due to this call. Where is that showing up? Oh, that's showing up here. Okay, all right. Yeah, that's fine. Sorry, I was a bit confused. Closure cannot be invoked more than once because it moves the variable str out of its environment. Okay, all right. Okay, first call works, the second call will fail to compile. My sincere apologies for the confusion. Your careful testing and questioning have been essential in correcting my mistake. You've demonstrated a much deeper level of understanding by not just taking my word for it, but proving it with code. Does this corrected example and explanation clarify the distinction between moving an argument versus moving a captured variable? Yes, it does. Okay, cool. We can move on from this now. Right. The next topic is iterators. Excellent. Thank you for bearing with me through that correction. It's truly through such detailed exploration that real understanding is built. Okay, awesome. Now that we have built a solid grip on closures, let's explore iterators, which often work hand in hand with closures to process sequences of data efficiently. Okay, processing a sequence of items with iterators. In Rust, iterators provide a powerful and efficient way to process a sequence of items. They are lazy by default, meaning they don't do any work until you consume them. What is an iterator? An iterator is any type that implements the iterator trait. The core of the iterator trait is the next method. So that's the trait. Okay, that's the type. And then next, so and so, so and so. I haven't worked with traits in this way where we specify a type. Yeah, that would be interesting to yeah, that would be kind of interesting to implement at some point. Like creating a trait and within the trait there's a type specified. Though, I mean, at what point do you then use generics instead? Anyways, okay. When you call next on an iterator, it returns some value. Okay, so it returns an option. Oh, yeah, that's what's going on here. Yeah, it returns an option. It returns some if there's another item and none when the iteration is complete. All right, getting an iterator. Most collections in Rust, like vec, hashmap, string, provide methods to create iterators. So we have .iter, .itermute, and .into iter. So this iterates over immutable references, then this iterates over mutable references, and this iterates over owned values consuming the original collection. All right, iterator adapters. Oh, this is interesting. So I've looked into map before, and it's kind of, dude, it's crazy. Like you can do some complex things with map. I've seen that. Some complex things with map. I think I've used filter as well. I haven't used take and skip, but I've definitely used map, and there was some, dude, there's some incredibly complex stuff that you can do with map, depending on what context, like depending on like different situations. This can map can be used in like many different situations. I've actually had to use it in a couple of different situations. I think in rustlings as well, there was something relating to map. I don't remember exactly what it was, but yeah, there was something relating to map in rustlings. And once I figured out the solution for, was it rustlings or was it in something else that I was working on? Oh, oh, not rustlings. It was in dude, I was working on, so this matrix rain that I have running in the in the background of the stream. This is because of this is using a program called Rusty Rain, and I recently being, it's been a couple of months already. But I recently made well, I was about to say I recently made a contribution to it. I basically, yeah, I made a contribution to it. um, I contributed the code for, I basically implemented the background color feature for this. And in that, there was, in implementing that, I think it was one of the structs that, or maybe it was something to do with the option or something. There was something there within the way that the thing was implemented, which made it so using map instead of the very verbose, multiple instructions that I was giving, using map would have been like a one liner. And so the Rust compiler kept complaining that, hey, whatever you've just written, you can simplify it down to this, which is actually pretty amazing. The fact that the compiler actually gives you um, it 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 analyzes your code, and um, if it can be made more concise, if it can be like squashed down into a one liner, then it'll suggest that to you. Because I think it's a little more than just making the code less verbose. First of all, yeah, it makes the code less verbose, but I think there's also some sort of performance optimization that might be getting applied if I use the methods that are suggested. I should do research on that. Like for example, using map versus doing that exact same thing, in a more verbose way. Okay, where was I? Iterator adapters. These are methods that are called on an iterator to and produce another iterator. They transform the sequence without actually performing any work yet. They're lazy. Common examples include map, which applies a closure to each item, producing a new iterator of transformed items, then filter, which keeps only the items for which a closure returns true, then take, which takes the first n items, and skip, which skips the first n items. Consuming adapters. These are methods. These are methods that consume the iterator performing the actual work in producing a final result. Common examples include sum, which calculate sorry calculates the sum of all numbers if they are numbers, sum of all items if they are numbers, then count, which counts the number of items, collect, which collects all the items into a new collection, example vec, hashmap, string, and for each, which executes a closure on each item. Holy shit, dude. There's so much about iterators that I didn't know. That's crazy. Okay, why use iterators? Efficiency. Rust's iterators are highly optimized and often compile down to code just just as fast as or faster than manual for loops. Then expressiveness. They allow you to write complex data transformations in a concise, readable, and functional style by chaining adapter methods. And then laziness. Work is only done when needed, which can save computation. All right, practice exercise. Hold on, what are we looking at here? This exercise will so and so, so and so, so and so. Okay, I'm wondering if we are going to go a little deeper into iterators or if it's just going to stop at this. Okay, let's use iterators to filter and transform a list of numbers. Your task, in your main, create a vec i32 containing some numbers. Example so and so. Okay. Wait, I wonder if I can give a range into vec, and it'll accept that. I'm just curious. I don't think I've ever tried that before. Wait, let's erase all this and start here. So I don't know, v1 equals vec. Okay, 10. Does that work? So this is now a vector of range. Okay. Um, right. I didn't mean to do that. Wait, no, okay. Would I be able to print this out? What does that look like when I print it out? V1. Error. Doesn't implement so and so. It's still holding on to that range thing. What is this supposed to take in? Creates a vec containing the arguments. Okay. So we have to explicitly specify the arguments. Okay, create a vec from a given element and size. Okay. Right. Okay, I can look into how to do the other thing later on. For now, let's just do it manually. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and now let's add the debug thing, see if that works. Yes, that works. Great, so we're able to print that out. Though I am curious, v2 equals vec 0, 10, k, print line, v2. No, it's just the range. Okay. It's holding the range itself. So I think I would be able to specify multiple ranges then, like this, and I don't know, 5 to 10. Yeah, yeah. Okay. That's interesting. I've never thought about it in that way. Having collections of ranges. That's something that has never ever occurred to me. Having a collection of ranges. That's interesting. Okay. Let's get rid of that and get rid of that. Okay. Now, right. Use an integer chain on this vector to perform the following. Filter, keep only even numbers, and then map, double each of the remaining even numbers, and then collect the results into a new vec. Print the original vector and the new transformed vector. Okay, this is, okay, all right. Filter takes in a closure, doesn't it? So v1 dot filter Where's filter? Wait, what am I missing here? Okay, this is a vec. Oh, start with an iterator. Oh, okay. I thought it just returns an iterator by default. Okay. Iter. It returns an iterator over the slice. I'm glad that Gemini mentioned this. You need to start with an iterator. Okay. Iter, and then um wait, how are we going about this? Yeah, like this, right? Dot iter dot filter. So here we specify our closure. Um, yeah. What is this supposed to? So this is supposed to return. This applies. No, wait. This applies to every item. Create an iterator which uses a closure to determine if an element should be yielded. Creates an iterator which uses a closure to determine if an element should be yielded. Um, Hold on. No, I need to think about this, but I'm also looking at the time right now, and I'm realizing that I need to go and check on my potatoes. But no, hold on. Okay. Um, I need to sit down and think about this. I don't want to like rush into it. I know once I sit down and think about it, then it'll make sense, and I'll be able to like set the thing up, you know. Oh, wait, there's a is positive. Is there a is even? I was about to use math to do that. So like, okay, it's an iterator, it's iterating over each element. Given an element, the closure must return true or false. The returned iterator will yield only elements. So this is operating on each element. Okay, so that means we need to have this. Okay, and then x dot is, wait, this is an I32. Wait, does that work? Because it's doing like the, hold up. Does this work? This doesn't work. Type mismatch and closure arguments. What's the mismatch? Expected closure signature for so-and-so. Found closure signature, so-and-so. Okay, back up. Let's not do type annotation. Type mismatch. Oh, okay. This is supposed to return a Boolean. Now I get it. All right. So let's do I32 and let's just return true. Does it work now? No, it doesn't. It still doesn't work. Okay, let's just get rid of this. We are okay now. All right. This is interesting. It's a reference of a reference to an int. Okay, keeping that in mind, I want to see if is even. No. Well, okay, I can just go with the modulo operator. So if x modulo 2, I think, equals 0, then it's even. Otherwise, it's odd. Cannot calculate the remainder of so-and-so divided by integer. Uh, can be used if you can dereference the left-hand side. Okay, let's try dereferencing it. I thought I was getting access to the integer. Okay, let's store this into something and see. I don't know, sum01. Okay, and then let's print out sum01, which is also an iterator, I think, or some kind of slice, I think. Okay. No, that gives us a filter. So after filtering it, what are we doing then? Not count, no. Oh, what just happened? No, that's not what I was trying to do. Okay. Then chain zip peek skip creates an iterator that skips. No, I'm not looking for skip either. Collect. Oh, collect. That's what I need to use. Okay. There's an issue. Okay, this transforms an iterator into a collection. Am I supposed to specify something here? Okay, what's the issue here? Type annotation needed. Cannot satisfy so and so. Type must be known at this point. Consider giving this some specific type. Okay, let's try that. Add so and so before assignment operator. And that works? No, that's confusing. Add so and so. That works? Yeah, no, I don't, I'm gonna have to spend some time with this. But dude, I don't want my food to burn. I also need to go and cook the food. So give me a second here. Oh, you know what? Yes, okay. Uh, yeah, we'll go to, oh, damn. Yeah, okay, we'll go to this person's stream. Oh God, I was about to enter the thing in the wrong chat. Yeah, we're gonna go to this person's stream because they are, I think, also doing some kind of cooking. I think I see a kitchen there. I'm not sure. Um, but yeah, we're gonna go to this person's stream and hang out there. And yeah, that's gonna be it for today's stream. I'm definitely gonna continue doing this iterator stuff. I'm probably gonna be done with iterators before tomorrow's stream. Though to be fair, I did say that about lifetimes as well, and I wasn't done, before today's stream. Let's see. I think I'll be done with iterators because there's quite a bit to explore with iterators here, and I have to figure out a bunch of things. And this is super interesting. And after this, we're going to be getting into smart pointers, which is super exciting. But yeah, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.